Welcome back to this series on topology. In today's video, we'll be continuing our discussion of quotient spaces. In particular, we'll be looking at how certain properties transfer from the space you start with to the quotient space. And second, we'll also be looking at how to tell whether certain surjective maps are actually quotient maps between topological spaces. In this video, I will presuppose that you know what a quotient map is, although I'll be briefly recapping the definition. So if you don't know what a quotient map is, you should probably watch the first video on quotient maps to get up to date. In general, you can find a playlist with all the videos in this series by clicking on the info thing that should appear right now. Let's start by remembering how we defined quotient spaces. The setup we start with is a topological space X and a set Y, along with a surjective map Q going from X to Y. And sometimes we'll write surjective maps with these double arrowheads just to remember that they are surjective. As I said, we suppose that X already has a topology on it, but for now Y is just a set. So the question is, what topology do we put on Y given the topology on X and this map Q? And now the definition for a quotient space tells us exactly what topology we should put on Y, namely the quotient topology. It says that a subset U of Y should be open if and only if its pre-image under Q is open in X. So this is how the quotient topology is defined on a set Y if we're given a topological space X and such a surjective function Q. On the other hand, if we start with topological spaces X and Y and a surjective map Q, and moreover the topology on Y satisfies this condition here in orange, then we will also say that Y has the quotient topology with respect to this map Q. Okay, so when we looked at other constructions, for example, product spaces and disjoint union spaces, we always listed properties that are preserved by the construction. And in those cases, basically all the properties we know and are interested in are preserved by, for example, taking products or disjoint unions of topological spaces. Hence, now the question is, does the same hold for quotient spaces? And the answer is no, not at all. For example, if X here is actually a manifold, then Y need not be a manifold. So it's totally possible to start with a really nice space, such as a manifold, and then take a quotient space and then get something that's not nearly as nice. To give a bit more detail on this point, let's remember that a topological manifold was defined to be a second countable Hausdorff space that is locally Euclidean of some dimension. Therefore, if we wanted Y to be a manifold, we would need this quotient construction to preserve each of these three properties. But in fact, it's possible to construct examples where any of these properties is not preserved by taking a quotient. For instance, one can start with a manifold and then construct a quotient space that is not second countable. Or you could start with a manifold and construct a quotient space that isn't Hausdorff, and so on. The take-home message here is really that when you're working with this quotient construction, you shouldn't just blindly expect properties from the original space to transfer to the quotient. You should always have a good argument for why that should be the case with the specific example you're working with. Oftentimes, this will boil down to checking the definitions for each of these properties individually, but there are also some propositions that make this process easier. Since this is a fairly technical topic, I'll just list one that comes in handy a lot. And it gives a sufficient criterion for the Hausdorff property to be preserved by taking a quotient. For this, we suppose we have the following situation. Suppose you have a topological space X and a quotient map Q to the quotient space Y. And moreover, we in addition suppose that this quotient map is an open map. That means that it is continuous and it takes open subsets of X to open subsets in Y. With this setup, the following equivalence holds, namely that this quotient space Y is a Hausdorff space if and only if a certain set, this set R, is closed in the product space x times x. What is this set R describing? Well, it's describing all the tuples x1, x2 that become identified under the quotient map Q. So this is all the tuples x1, x2 in the product x cross x, such that Q of x1 is equal to Q of x2. One way to think about this set is as a relation, and it relates 2 points in x precisely when they become identified by the quotient map Q. So this relation will be very big if the quotient map identifies a lot of points, so smooshes a lot of points from x together, and it'll just be the identity relation if the quotient map is injective and doesn't identify anything. Hence, this proposition is now saying that provided the quotient map is open, the Hausdorff property for the quotient space doesn't really care about how large this relation R here is. It just cares whether it's closed in the product x cross x. Okay, let's try to prove this, starting with the left to right direction. For this, we suppose that Y is actually a Hausdorff space. And we're now required to show that this set R is a closed subset of the product x times x. Remember that the definition of being a closed subset is that the complement of the set in question is an open set. Therefore, we take some x1, x2, which does not lie in this set R. So that means that it lies in the complement. And now we want to find a neighborhood around this point that is disjoint from this set R. Or another way of saying this, which is maybe more clear from the open set perspective, we're taking a point in the complement of R, and we want to show that there exists a neighborhood around that point that lies completely within the complement. All right, so now we use the fact that we know that Y is a Hausdorff space. And if you remember, being Hausdorff means that for any two distinct points, you can find open neighborhoods around each, such that those open neighborhoods are disjoint from one another. In particular, we can take the points Q of x1 and Q of x2. So these are distinct because they are not elements of R. If you look at the definition of R, these are exactly all the tuples such that Q of x1 and Q of x2 coincide. So if we take something outside of R, it means that they have to be distinct. Now we have two distinct points in a Hausdorff space, so it follows that there exist neighborhoods V1 of Q of x1 and V2 of Q of x2, such that these two neighborhoods are disjoint from one another. Okay, and now I claim that if we take the pre-image of this open neighborhood V1 times the pre-image of the open neighborhood 2, then this is actually a neighborhood of the tuple x1, x2 in the space x cross x. Let's think about why this is the case. Well, by definition, these neighborhoods V1 and V2 are open sets in Y. Therefore, since the map Q is a continuous map, it means that their pre-images are also going to be open sets in X. So each of these individually is open in X. Therefore, their product will be an open set of the product space because the product topology is generated by all of the products of this form. So that shows that this set I've written down here is indeed an open set of the product x times x. The only thing we need to check in addition is that this point x1, x2 is actually contained in this set. And this is the case because Q of x1 is contained in V1 and Q of x2 is contained in V2. So if we take preimages, this means that x1 is contained in the preimage of v1, and x2 is contained in the preimage of v2, just by the definition of what a preimage is. Okay, so we verified this claim. So we found an open neighborhood around the point x1, x2. Now the final thing to check is that this neighborhood we found is actually disjoint from R, meaning that it is contained in the complement, showing that for an arbitrary point in the complement, we can find a neighborhood around it, still contained within it, which will then show that this complement of R is an open set. Let's assume, for the sake of contradiction, that there is actually a point z1, z2, which lies in the intersection of this neighborhood we've defined and R. Well, what does this mean? Since z1, z2 lies in the preimage of v1 times the preimage of v2, this means that q of z1 is an element of v1, and q of z2 is an element of v2. But now observe that by assumption, v1 and v2 are disjoint from one another. Therefore, it's impossible for q of z1 to equal q of z2. On the other hand, the points in R are precisely those tuples such that q of the first component is equal to q of the second component. Thus, on the one hand, q of z1 is definitely not equal to q of z2 because of this condition, but because z1, z2 lies in R also, this means that q of z1 is equal to q of z2, and that is a contradiction, which shows that, in fact, there cannot be such a point z1, z2 in the intersection. Okay, so in summary, we've shown that we can find an open neighborhood. In this case, it's this set of the product of the preimages of an arbitrary point in the complement of R, such that that open neighborhood does not intersect R, or in other words, such that that neighborhood is contained entirely within the complement. This then shows that the complement of R is actually an open set of the product x times x, which by definition means that R is a closed set. And this proves the left to right direction. Notice that for this direction, we didn't actually need the assumption that this quotient map is an open map. Let's now turn to the right to left direction. For this, we suppose that R is closed. Now the goal is to show that Y is a Hausdorff space, so we need to apply the definition of what it means to be Hausdorff. For this, we take y1 and y2 distinct points in Y. To be Hausdorff, we would have to find two neighborhoods, one around y1 and one around y2, such that those neighborhoods are disjoint. Okay, so we're working with this quotient map, which goes from x to y, and we know that this quotient map is surjective, which means that y1 and y2 will be the image of some point in x. So I'll write this like this: find x1 and x2 in x, such that q of x1 is equal to y1 and q of x2 is equal to y2. And just to repeat, this is possible in this case because Q is a surjective map. We now observe that because the points y1 and y2 are assumed to be distinct, the tuple x1, x2 does not lie in the set R. Again, this is just a definition of R, because R only contains tuples whose images are the same under the map Q. All right, so we found this point which does not lie in R, but now remember that we're assuming that R is closed, which means that its complement is open, and this x1, x2 is a point in the complement of R. So this means that there exists a neighborhood, which I'll call U, of x1, x2, that is disjoint from R. Or in other words, the neighborhood U is entirely contained within the complement. Now we have to remember what open sets are in product spaces. Recall that the product topology is generated by all individual products of open sets of the original spaces. In particular, this means that U is actually of the following form. It's a union over some sets U1i times U2i, where these U1i's and U2i's are open sets in X. Now, since x1, x2 is contained in U, this means that x1, x2 is contained in this union, and in particular, that also means that x1, x2 is contained in one of these products, U1i times U2i, for some specific I. That's just the definition of what it means to be contained in a union. So x1, x2 is an element of U1i cross U2i for some I. Moreover, because U is disjoint from R, and U1i, U2i is a subset of U, it means that U1i, U2i has to also be disjoint from R. Okay, now as a final step, we consider Q of U1i and Q of U2i. And I claim that these are going to be the disjoint neighborhoods in Y that we were looking for originally. So first of all, each of these sets is an open set. Why is this? Well, we know that U1i and U2i are individually open sets of X because that's the way that the product topology is defined. Moreover, we assume that Q is an open map, meaning that it takes open sets to open sets. So Q of U1i is an open set because U1i is an open set in X and Q is an open map. And similarly for Q of U2i. That shows 1/3 of what we need to show. Next, we observe that Y1 is contained in Q of U1i. Why is this? Well, this is because X1 is contained in U1i, and moreover, Q of X1 is equal to Y1, which means that Y1 needs to be contained in the set Q of U1i. Similarly, X2 is contained in U2i, and Q of X2 is Y2, so Y2 needs to be contained in Q of U2i. Together with the fact that these are open sets, this shows that these are indeed neighborhoods around Y1 and Y2 respectively. The last thing we need to show is that they are disjoint. But this simply follows from the fact that this set here is disjoint from the set R. In particular, suppose you had some point Q of Z1 contained in this Q of U1i, and some point Q of Z2, which is contained in the set Q of U2i. Now, if these were equal, then we could just look at the point Z1, Z2, which is an element of U1i times U2i, and for this element, it holds that Q of Z1 is equal to Q of Z2, which would mean that this point was actually contained in R. But this contradicts the fact that this set U1i times U2i is actually disjoint from R. Hence, this contradiction shows that it's not possible to have a point in the intersection of these sets. Okay, so this proof is pretty elementary in the sense that you're just applying definitions, but it's maybe a bit convoluted, so let's go through it one more time. So we started with the assumption that this set R is closed, and we took distinct points y1 and y2 in Y, and to show that Y is Hausdorff, we have to find two neighborhoods, one around y1, one around y2, that are disjoint. Now, by the fact that Q is a surjective map, we can find points x1 and x2 in X, such that y1 is the image of x1 under Q and y2 is the image of x2 under Q. We then observe that this point, x1, x2, does not lie in R because y1 and y2 are assumed to be distinct, which means by the fact that R is a closed set that there exists a neighborhood of this tuple x1, x2 that is disjoint from R. Finally, we used the definition of the product topology to find a set of this form, u1i times u2i, in which this tuple x2 lives, and then we individually mapped u1i to y using q and u2i to y using q. Then, using the fact that q is an open map, these sets here are actually open neighborhoods of the points y1 and y2, and moreover, they are disjoint from one another because this product set here was chosen in such a way that it's disjoint from R. And with that, we conclude the proof. Before moving on, I'd just like to emphasize why this proposition is useful. It's useful because when you're taking a quotient of some space, you probably know more about the space X than you do about the quotient space Y. So in particular, you probably also are able to find out things about the product of X with itself. So in that case, it's easier to check whether a certain set is closed in the product space rather than directly checking that the quotient space Y is Hausdorff. But beware that this equivalence here only holds if Q is in fact an open quotient map, and by no means all quotient maps are open. This perhaps raises the question of what the relationship is between quotient maps and open maps in general. And this is something we'll look at in more detail in what follows. To do so, we'll need to introduce some more terminology. For this, we slightly change our setup. So we suppose that we have just sets x and y and some function q between x and y. We will now introduce a name for pre-images of single points in y under the map q. And these will be called fibers of the map q. Hence, given any point y and y, we can consider its fiber, which is just the pre-image of that single point under the map q, or in other words, it's all the points in X which map to that point via Q. Finally, if we're given some subset U of X, we will call this subset saturated with respect to the map Q if U is actually the pre-image of some set V in Y. Perhaps a drawing will make this a bit easier. So here we have our set X, and here we have our set Y. And now suppose we have some point y and y, then we can consider the fiber over y, which are all the points in X which map to y via Q. Maybe we also have some second point z, which will have its own fiber. Maybe it looks like this. And now we could take some arbitrary subset of X and ask whether it's the pre-image of some subset in y. For example, if we would take the subset of X that contains the orange and the red sets, then this would indeed be the case because this set would be the pre-image of the set in Y that contains Y and Z. And now we would call this green set saturated with respect to the map Q. On the other hand, it's possible to find subsets of X which are not the pre-image of any subset of Y. For example, if I just take half of this red set here, then this is not the pre-image of any subset of Y as I've drawn it here in this picture. Hence, in this case, this green set would not be saturated with respect to the map Q in our small example here. The reason we care about these definitions is that they allow us to characterize quotient maps in a nice way. This is what this proposition is stating, and probably at first reading it sounds more complicated than it actually is. Basically, it's just giving you a way to think about quotient maps in terms of these saturated open subsets, or also in terms of saturated closed subsets. It says that if we have some continuous surjective map Q from X to Y, and here we're now assuming that X and Y are already given topological spaces. So if we have such a map, Q, that is continuous and surjective, then this map Q is a quotient map if and only if the following holds, namely if Q takes saturated open subsets of X to open subsets of Y, or alternatively, if Q takes saturated closed subsets to closed subsets of Y. One way to think about this is that this is a weaker form of openness for the map Q. So instead of taking every open set of X to an open set of Y, or alternatively taking any closed set of X to a closed set in Y, being a quotient map only requires taking certain open subsets to open subsets, namely those that are saturated, or alternatively taking certain closed subsets to closed subsets, again, them being those that are saturated. Perhaps seeing the proof here will help digest the statement. So first, assume that Q is actually a quotient map. Then, by definition, a subset U of Y is open if and only if the preimage of U is open in X. All right, so now we need to check that Q takes saturated open subsets to open subsets, and also that Q takes saturated closed subsets to closed subsets. So first, we let V in X be a saturated open subset. So in other words, by the definition of what it means to be a saturated subset, V is just the preimage of some, I'll just call it U1, where U1 is a subset of Y. Okay, but this subset V was assumed to be open, so also this preimage is open, and from this it now follows that U1 is open by the definition of what it means to be a quotient space. But, well, U1 is just equal to Q of V, or Q of Q inverse of U1. So we have shown that Q takes saturated open subsets V to open subsets U1. Okay, so that shows one direction for these saturated open subsets. Now, if instead of an open subset, we'd started with a saturated closed subset, then again, V would be of this form. It's a preimage of some subset U1. Now, one can show that this definition of quotient map actually also holds for closed subsets. So U sub Y is closed if and only if the preimage is closed in X. And then using, again, this equality down here, this shows that saturated closed subsets are taken to closed subsets. So if you want, you can think about this in more detail, but it's essentially the same proof, just replacing the words open with the words closed. All right, so this shows that if we have a quotient map, then it takes saturated open subsets to open subsets. Now we want to show the converse, that if we have a continuous surjective map, Q, that does this, that it then means that this is a quotient map. Okay, so assume that Q from X to Y is continuous and surjective. Okay, we need to show that if we have some subset U in Y, that this is open precisely when the preimage of U is open in X. In order to do this, we assume either that Q takes saturated open subsets to open subsets or saturated closed subsets to closed subsets. So I'm just, again, going to do one version. Suppose Q takes saturated open subsets to open subsets. Okay. Let's do the first direction of this equivalence we need to show. So if U sub Y is open, well then the preimage of U is open in X by continuity. So that takes care of one direction. Conversely, if the pre-image of some set U is open in X, well, this thing here is precisely a saturated open subset of X. So this implies that Q of Q inverse of U is open in Y. But on the other hand, Q of Q inverse of U is equal to U, and this follows because Q itself is surjective. This is something I'll also leave to you to think about, but the picture kind of looks like this following. So if we have some subset U of Y, and we first take its pre-image, so that gives us some subset of X, then because Q is surjective, it means that any point that occurs in this subset has some point in the subset of X that maps to it. So if you now again map forward with Q, you'll end up with the same subset you started with. Another way to think about this is what can go wrong with this process of taking a pre-image and then mapping back. Well, if you had some point in Y that was not mapped to by any point in X, then if you would take the pre-image, that would be empty. And so if you then map the empty set forward with Q again, you would again get the empty set. So it's possible if you have a non-surjective map to start with some subset here of Y, take the pre-image, map forward, and end up with a smaller set than you started with. But this is only the case if Q is not surjective. Okay, so with that we're actually done with the proof, because we've shown that if we assume that we have some continuous surjective map, then this condition here, this equivalence, will hold provided that that map takes saturated open subsets to open subsets. I've again left out the case where we assume that the map takes saturated closed subsets to closed subsets, because this is very similar, and we'll see in a brief moment an equivalence of defining quotient maps also in terms of closed subsets, so this actually then just becomes the same proof. Maybe now that we've seen the proof, the statement is also a bit clearer. It's just giving us a different way of thinking about quotient maps as maps that take a special collection of open subsets to open subsets. And in this case, it's the saturated open subsets. Or alternatively, we can also think of quotient maps as being those maps that take the saturated closed subsets to closed subsets. Now, one consequence of this proposition that's immediate is that any map that is continuous and surjective and takes all open subsets to open subsets is a quotient map. Or conversely, any continuous surjective map that takes all closed subsets to closed subsets is going to be a quotient map. Using our terminology, this is saying that surjective open maps are quotient maps, and also that surjective closed maps are quotient maps. Hence, the case we were considering before for the preservation of the Hausdorff property, that we have an open quotient map, this is basically the same thing as saying that you have a surjective map that's also open. We saw before that quotient maps don't preserve many properties. For example, they don't preserve second countability or Hausdorffness or being locally Euclidean, but they do still have some properties which are useful to know. The first of which is that any composition of quotient maps is again a quotient map. This is something you can verify directly from the definition. It's basically just stringing together two equivalences. The next property is that injective quotient maps are actually homeomorphisms. Why is this? Well, we know that quotient maps are surjective, so if we have an injective quotient map, this is actually saying that we have a bijective continuous map from the space X to the space Y. This is not quite yet enough to be a homeomorphism, but the definition of open sets in the quotient space actually makes this a homeomorphism, because it's saying that a subset of Y is open precisely when the pre-image is open in X. This is also the definition for what it takes to be a homeomorphism if you have a bijective map from X to Y. Okay, next, this is the property I was alluding to before when I said that quotient maps could also be defined in terms of closed subsets of spaces. So if we have a quotient map Q from X to Y, then a subset K of Y is closed precisely when the preimage of K is closed in X. The proof of this basically, again, just involves writing out the definition and taking complements, as is usual for when you want to prove things for closed subsets and you have the corresponding definitions for the open subsets. Next, property D concerns how we can restrict quotient maps on certain spaces. So it's saying that if we have a saturated open subset of X, or alternatively a saturated closed subset of X, then we may restrict the quotient map to that set in the domain. And moreover, the resulting map will again be a quotient map. So in general, it's not possible to restrict to an arbitrary subset of the domain and still have the resulting map be a quotient map. In order for this to work, the subset you're restricting to has to be saturated. Either it has to be a saturated open subset or a saturated closed subset. Finally, the last property gives us another way of constructing new quotient maps from old ones. So suppose that we have some family of quotient maps Q alpha from spaces X alpha to Y alpha. Then we can form a quotient map by taking the disjoint union of all these individual maps. So we get a continuous map from the disjoint union of the X alpha to the disjoint union of the Y alpha. And if the original maps were all quotient maps, then also this disjoint union of maps, Q tilde, will be a quotient map. Intuitively, this makes sense because in the disjoint union, all of these spaces are sort of sitting separately next to one another. So if we have some properties on individual maps between these spaces, they should be preserved by this construction. To fix some of these ideas I've just presented, let's look at some examples. So the first example we'll be considering is a map Q from Rn+1 without the origin to Sn, given by mapping X to X divided by its absolute value. For simplicity, I'm going to choose n to be equal to 1 so that I can draw this stuff nicely. And in that case, we are considering R2 without the origin, and we'll be mapping to S1, which is just the unit circle. Okay, and I'll indicate the fact that we don't have the origin by just leaving a blank there. All right, so what is this map Q doing? Well, it's taking any point, in our case in R2, and it's mapping it to the normalized version of that point, so the corresponding point that lies on the unit circle. Geometrically, what's happening is that we have this ray going out from the origin to the point, and we're mapping that point to the place where this ray intersects the unit circle. So if this is x, then this point on the unit circle would be q of x. Notice that any point on this ray will be mapped to the same point on the unit circle by q. Okay, so now what we're going to do is we're going to think about what the saturated open subsets are of the space R2 without the origin. Remember from the definition that saturated sets are just those sets that are preimages of some subset of the second space. To find these, it's sufficient to consider what fibers the map has, and then think about the unions of those fibers. For example, if I take some arbitrary point here on Sn, then I can consider the fiber over that point, which will just be this ray that goes off to infinity, going through the point on the circle. From this one can infer that the saturated sets of R2 without the origin with respect to this map Q are going to be unions of these types of rays. For example, I could look at all the rays that sort of span up an angle, and this would be a saturated set of R2 without the origin, because it's the pre-image of this segment of the circle. Conversely, if I take any subset of the circle, its pre-image will be some union of such rays. Okay, so we've determined that the saturated subsets of R2 without the origin with respect to Q are precisely unions of these rays, so the open saturated subsets of R2 without the origin will be open sets that are also unions of such rays. All right, so let's suppose we have some union of such rays that happens to be an open subset. Now, if we project this via Q down to the unit circle, what we would get is an open segment on the unit circle. Basically because this original set was an open set in R2. So you could check this in detail, but I think it's intuitively clear that if you start with such a bundle of rays that is open, then if you project down, what you get is an open segment. Now, if this bundle isn't like adjacent to each other, but consists of multiple individual open bundles, then what you'll get by projecting are unions of these open segments of the circle. So this would show that the map Q takes open saturated subsets to open subsets of the unit circle, meaning that it's in fact a quotient map. So I'm aware that this illustration wasn't very rigorous, but I hope you get the intuitive idea about how to think about these quotient maps in terms of these saturated sets. So if you want to think about this in more detail, you could try writing down a very detailed proof of why this map Q actually does take these saturated open subsets to open subsets of the circle by using all the definitions of the topologies in question. Our second example concerns the construction of a cone over a space X. Remember that we defined the cone, Cx over a space X, as the following quotient. So first we take the cylinder over X. So this is just X times the unit interval. So here I'm thinking of this top bit as being X, and here on the side we have the unit interval. Now we take a quotient where we identify all of the points that have coordinate 0 in the unit interval. So we're basically identifying all the points that lie in this bottom copy here of X to a single point. And this thing is then the cone over X. Now, as I've suggestively indicated, we can just think of this part here on top as being a copy of X embedded in this construction. To do this rigorously, we could call this set here on the top X star, and here this set would be X times the singleton 1. And we now observe that Q maps X times the singleton 1 to X star. So X star is actually equal to Q of X times the singleton 1. Or conversely, X times the singleton 1 is equal to the pre-image of X star. So both of these things hold in this case. Okay, but this now means that X times the singleton 1 is a saturated set in this space X times the unit interval. Moreover, it's a closed subset because the singleton 1 is closed in the unit interval, and X is also closed in X itself. Therefore, the product X times the singleton will be a closed subset of the product space X times the unit interval. So in fact, this is not just a saturated subset, but a closed saturated subset. And by the previous properties we saw, this means that we can actually restrict this quotient map Q to this closed saturated subset. So consider Q restricted to X times the singleton 1. This is a map going from X times the singleton 1 to this set X star, which is a subset of this cone. And finally, we just observe that this X times the singleton 1 is homeomorphic to X itself. This is something you can easily check for yourself. The fact that they're isomorphic as sets should be clear because we're mapping x to x, 1 for each x in x, and this is clearly bijective. So the only thing you need to check is that this bijection is actually also compatible with the topologies on the corresponding spaces, where on the top we're considering the subspace topology of this set x times 1 inside the product space x times the interval, so in here. And on the bottom we're just considering the topology we have given on x. Now if you recall the definition of subspace topology, the open sets in the subspace topology are just intersections of open sets of the larger space with the subset. On the other hand, the open subsets of this space here are given as products of open sets of x with open sets of I, but because we're in the end intersecting with x times a singleton, the open sets of I kind of don't matter for what the open sets of this subspace are. So you'll just recover all the open sets of x again, which justifies this homeomorphism here. Again, you should probably check these things in detail to become more familiar with these constructions, but for the moment it's not the interesting part of this example. Resuming our main narrative, we started with this quotient map Q, and we observed that this subset here, x times the singleton 1, is actually a closed saturated subset of this product space. Therefore, we can restrict Q to this subset, and we get a map going from x times the singleton 1 to x star. And we also noted that x times the singleton 1 is actually homeomorphic to the original space x. Now finally, we can also observe that this map here is actually also a homeomorphism. Why is this? Well, if you look at the definition of the quotient we're taking, we're not touching any of the points that don't have coordinate 0. So as long as we're not in the section of this product where we have coordinate second coordinate 0, we're actually just injectively mapping whatever we have on the left-hand side to the right-hand side. So in particular, this restriction of Q is injective, and we saw previously that injective quotient maps are homeomorphisms. Okay, so in summary, we have these two homeomorphisms, one from x to the space x times the singleton 1, and then one from the space x times the singleton 1 to this x star. We can compose these, which shows that x is actually going to be homeomorphic to this x star lying in the cone. And this justifies our intuitive identification of this x star with the original space x. So we can really think of x as just being this base part of the cone. The final example we'll look at is the map that maps the closed unit interval to the unit circle. So in pictures, if this is the unit interval, then Q is mapping this to the unit circle, where Q of 0 is equal to Q of 1. And we can write this down nicely by using this complex notation and just taking this exponential map where we map s in the unit interval to e to the 2 pi I s. But if you don't like thinking about this in terms of the unit circle as being a subset of the complex plane, then you can also just intuitively think about taking this unit interval and wrapping it around the circle as I've indicated. Okay, so we have this map which, actually I noticed this is no longer called Q, but actually it's called omega. So we have this map omega, and we want to check whether this is in fact a quotient map. As it is given, it is just a map going from the unit interval to S1, and we've defined it in this way, but we actually don't yet know whether it's a quotient map or not. So what we want to do is we want to check whether this given map is actually a quotient map. Okay, so we need to remember the definition of what it means to be a quotient map. So first, the map needs to be continuous, which this map is because this exponential function and multiplying by stuff is continuous. The second thing a map needs to be in order to be a quotient map is surjective, and this is also the case because any point in the unit circle has a preimage in this closed unit interval. Therefore, the only thing we need to check is whether this quotient map actually satisfies the condition that the subset U of S1 is open if and only if the preimage omega inverse of U is open in I. Okay, so if we have some open subset of S1, then its preimage will be open in I by continuity. So this direction here, this is just continuity. And we assume that we know that this exponential function is continuous, for example, from like an analysis course. Conversely, we need to check that if we have some subset of I that is the preimage of some subset U in the unit circle, and this is open, then also its image is open in the unit circle. Okay, so that sounds a bit convoluted, so we let omega inverse of U be open in I. And now we need to show that this means that also U was originally open in S1. Let's think about taking some arbitrary subset U in S1 and considering its preimage in I, which we're assuming is like an open set. So this is like omega inverse of U. Now, what we want to do is show that the original set U is open. So we pick some point Z in U. And we want to find a neighborhood around it such that that neighborhood is entirely contained within U. Now there are two cases. In the first case, Z is as I've drawn it here, so it's not the point where we have Q of 0 being equal to Q of 1. And in this case, Z will actually have a unique point that maps to it from I. So there'll only be a single point, I'll maybe draw it here, Q inverse of Z, in the preimage. And now by assumption, the preimage of U under omega is an open set, which means we can find a small neighborhood around this point, Q inverse of Z, that is still entirely contained within the set omega inverse of U. All right, so we started with a point Z in the unit circle. We said that if Z is not this special point in the unit circle, then it has a preimage which just consists of a single point. And in that case, we can find a small neighborhood around the preimage that is contained within the entire preimage omega inverse of U. Now if you think what happens if we map this small neighborhood we found around Q inverse of Z back to the unit circle via omega, what we'll end up with is actually a wedge, which I'll draw here on the outside so as not to make this drawing more complicated. We'll find a small wedge around Z. Moreover, because this original neighborhood here is entirely contained within the preimage omega inverse of U, it means that this wedge we find by mapping this neighborhood back is entirely contained within the set U. Moreover, the wedge of this type is actually an open set of the unit circle, which one could again rigorously check by going through all the details. And this shows that for a point Z in U, we found a neighborhood around it that is entirely contained within U, meaning that U is an open set for this case. There's a second case where we would have chosen this special point here, which maybe I'll call X. And the preimage of this special point is actually consists of 2 points, namely of the points 0 and the points 1. But also in this case, we can find a neighborhood around these 2 points, which will actually, in this case, I'll maybe draw it in a separate picture. So this is the point 1 and this is the point 0. And the neighborhood we're selecting consists of 2 little half-open intervals around these 2 points. And if we map this back to the unit circle, what we end up with will be the union of these 2 little half-open intervals. And that's exactly, again, going to be an open segment of this unit circle that by assumption will be contained entirely within the set U. So no matter which point we choose in the unit circle, we can find an open neighborhood around it in the form of this open segment, and this shows that the set U is actually open. Thus, indeed, this omega here is actually a quotient map. Again, here you notice I'm skimming over a lot of the details because doing this rigorously would take like a ton of time. But if you're not satisfied with this intuitive explanation, you should really dig into the definitions and go through everything step by step and check that it really works. Later on in the course, we'll have tools, for example, the closed map lemma, which will allow us to say that this omega is a quotient map without having to dig into all the details. Moreover, in the next video on quotient spaces, we'll actually be thinking about quotient spaces more abstractly in terms of universal properties, and this also has the advantage that you don't have to dig through all the definitions when you're trying to prove that certain things are quotients or that they're isomorphic, and so on. To wrap up this video, let's just briefly go through some more properties that hold for quotient maps that we've basically already discussed, but I'd just like to summarize them because they're important. So the first property says that if we have a continuous surjective map from X to Y that is either an open map or a closed map, then it is in particular a quotient map. I basically already gave the proof for this when we were discussing a previous proposition. We know from before that quotient maps are precisely surjective continuous maps that take either open saturated subsets to open sets, or alternatively take closed saturated subsets to closed subsets. In particular, this means that if you have a continuous surjective map that takes all open subsets to open subsets, or all closed subsets to closed subsets, that this is automatically going to be a quotient map. And that proves this proposition, which is useful to know because it gives you a sufficient criteria for something to be a quotient map. Namely, you just have to check that a map is either open and surjective, or alternatively, you could also check that the map is closed and surjective. As an example of this, we can consider the projection pi I, which goes from the n-fold Cartesian product of spaces x1 up to xn to the individual space xi. Okay, from our video on product spaces, we know that pi I is actually an open map. So in particular, this implies that pi 1 is also a quotient map. Intuitively, this means that if you have a product space, you can view each of the factors of the product as a quotient of this product space. I'd like to conclude with this proposition that summarizes some of the results we've seen previously in this series. So repeatedly, we've seen that if we have a continuous map that is either open or closed, then if this map satisfies some additional properties, then it's one of the special types of maps we're particularly interested in. So for example, if we have a continuous map that is either open and closed and is in addition injective, then it is a topological embedding. If the map that is continuous and open or closed is in addition surjective, then we've just seen that this means that it's a quotient map. And finally, if such a map is bijective, then it means that it is a homeomorphism. This ties in with the theme I mentioned in the video on open and closed maps, that often the properties of being open or closed are intermediate to prove properties about maps that we're actually interested in, such as them being homeomorphisms or quotient maps or embeddings. So that's how this story about continuous maps that are open or closed and surjective being quotient maps, how this fits into the broader picture. Okay, with that, I'm done with what I wanted to say in this video. In the next video, we'll again be looking at quotient spaces, but from a more abstract perspective. In particular, we'll be giving the universal property for quotient spaces, and we'll also be giving a nice way to show that certain quotient spaces are isomorphic, just based on a simple criterion involving their individual quotient maps.